Hello and welcome to Mystery Science. I'm Mr. E and you're joining us for the first video in this playlist about radioactivity. This lesson we're going to be looking at atomic models. Now if you haven't seen the first video of the playlist, don't worry, it's just an overview of the whole playlist itself. If you want to know what's going on, then please do have a look at that video. If not, carry on and just watch it sequentially, but I do recommend sitting and watching through the playlist because it will put it all in a nice little package for you. So let's have a look at atomic models. What are we going to learn in this lesson? Well, let's have a quick look at the objectives. We're going to describe the structure of an atom in terms of the nucleus and the electrons. We're going to be able to state where most of the mass of an atom is. We're going to be able to state the sizes of atoms and small molecules in relation to the world around us. We're going to be able to describe the early model of an atom. And now, don't worry, this crosses over with the chemistry, so I'm not going to go into a whole heap of detail. That's already done for us by the chemists. But what I am going to do is I'm going to look at this in terms of the nucleus and what it means for our understanding in physics of the atom and the radioactive decay. We're going to have a look at how and why our model of the atom has changed over the centuries, and we're going to have a quick look at a timeline. Once again, this is covered in much more detail in the chemistry section, but it overlaps in physics purely because the nucleus of the atom is really important for the physicists. The chemists are more interested in the electrons, how the electrons are interacting with other electrons in other atoms. Chemists, eh? This is the particle theory. We've all seen this before. We've seen that solids are packed, closely packed, very dense materials. Now, any of my students will tell you that they cringe every single time I start to talk about particle theory. Why, Mr. E? Why would your students cringe? Well, it's because I do this. I start to talk about the particle model and I represent the particles inside the solid as these two very, very large particles joined together like this at a temperature called absolute zero, 0 Kelvin, minus 273 degrees. You will find that everything stops. All of the particles inside everything in the entire universe will stop at this temperature. There is no movement. Now, we believe that this is a theoretical temperature. Nothing actually really stops. What you've actually got is very, very slight movement, and so you have a temperature that is just above this absolute zero. But in a normal solid, our particles are vibrating. They're rubbing together. They're in contact with each other, at least the bonds are. The electrons are intertwined, but the atoms themselves are jiggling around. Now this is a solid. Now a solid is rigid. You can't change its shape. It's not fluid. You can't pour it. And that's because if you look at all the atoms as they're arranged in this section, you can't squash it and you can't bend it really because the atoms have got nowhere to go. They're all really stuck together. When you get into a liquid, what happens is you have these particles, they're vibrating more and more as you heat them up. And then when you heat them up enough, all of a sudden the bonds start to break, and all of a sudden now these particles can slip over each other. And this means that actually you can start to change the shape. You can change the overall shape of the liquid, and it's now going to take the shape of whatever container it's in. It's still bound by gravity, and you can pour it. They can flow over each other, so they can flow. Now, if you increase the temperature of this enough, this is where things get cringy and the dad dancing comes. Eventually, the bonds break, and we end up with these particles flying around all over the place. This is probably doing hell for the autofocus for my camera. But these particles now fill the entire screen. There we go. And they also fill whatever container they're in. Now, why is this important? And it's important because we can now understand why gases will do what gases do Liquids do what liquids do, and solids do what solids do. Now, the question though is, okay, so we've got these particles and they fit in these nice little boxes all closely packed together. What are they made of? What are these particles? Are they, just like this, actually little balls? And for a long time, and we'll talk about how long, we thought, yes, they are. But turns out, no. So let's go on a little journey about how we discovered what the atom actually is. Let's have a quick look at the atomic theory through the ages. Now, around about 400 BC, some really smart Greek dude known as Democritus, he sat there with his amazing beard and he pondered. He was a very well-travelled, learned man. For an ancient Greek, he travelled around a lot. He wrote about the Egyptian scholars. He travelled to the Far East, all the way to India and South China. So he had talked to a lot of people and gathered a lot of theories. And so he thought a lot about putting all these things together. And he surmised that actually, if you take an object, let's say this, just any object, and I chop this object in half, and I throw half of it away, I'm left with half a mouse. If I chop that mouse in half again, I've got a quarter of the original mouse left. And then if I keep chopping it, eventually I'm going to get to a particle that's so small I can't chop it anymore. It has to be made of an indivisible particle. And he called this atomos, which is Greek, ancient Greek, for indivisible. Now this atomos theory was around for a long time. This was 400 BC. It wasn't until John Dalton came along in 1803. That's over 2,000 years later. That's 2,200 years later, in fact. Remember that Democritus' theory was all about thought. He didn't actually know this stuff. He couldn't prove it. John Dalton came along and he did a series of experiments. And this is why science is important, and we teach you about science. It's not necessarily about the knowledge, and it's not necessarily about applying the things we teach you, but it's about the way you think. It's about taking on information and going, well, how can I test this in the real world? How do I know this is true? John Dalton did exactly that. He took this 2,200-year-old theory and he said to himself, can I prove that this is true? And he did. What he did was he took water and he broke it down into its constituent parts. Now you may or may not know, hopefully you do, that water is made of 2 hydrogen atoms and 1 oxygen atom. Now in the 1800s, the 19th century, they didn't know this. And so he took the water, which is a well-known solvent, and he broke it apart. And he found that he always got twice as much hydrogen as oxygen when he broke it apart. So he realized, yes, water must be made of 2 parts hydrogen, 1 part oxygen all the time. And he was right. And he couldn't break it down into any other ratio. And he couldn't break the water down or the oxygen down or the hydrogen down into anything else. So he decided, aha! Democritus was right. These are indivisible, tiny particles that no one can see, but no one can break down. It's the most fundamental particle. You can't get smaller than this. Ha ha! I have solved the universe. Hooray! Now, unfortunately for Dalton, that's not technically true. In 1904, 100 years later, J.J. Thomson came along and did another experiment. He charged a substance up with really high voltage, and this made a stream of particles come off of a substance. Now this stream of particles, he thought maybe, oh, these are teeny tiny atoms of something. They're very much smaller than I was expecting. And then he realized that the end of his oscilloscope, the thing that he was using to propel these things, was glowing. It was glowing green because he had a phosphorescent screen. And then he thought, well, I wonder what I could do with these. And he put a magnetically charged plate above the oscilloscope. And what happened was the beam deflected. It moved because the beam was charged. And he realized that this beam of particles is smaller than an atom. So they must have come from the atom. So they're smaller than an atom. These are subatomic particles. Subatomic simply means smaller than an atom. So a subatomic particle is a thing that makes up an atom. So he thought John Dalton wasn't quite right. There is something smaller than an atom. It's these little electron things, and they're negatively charged. Hurrah! So therefore, what is an atom? And he developed this, the plum pudding model. He thought everything in this atom is positively charged matter, but it's got these little splodges of electron stuck inside it, just like a plum pudding. If you don't know what a plum pudding is, don't look it up. It's gross. Basically, it's like a tea cake. It's a really thick, suety thing with plums in it. And he likened all these plums dotted throughout the pudding as the electrons inside this atom. Wow! So now we've got a sphere, a spherical model with electrons inside it, which are somehow able to just leap out through electric charge. A few years later, Ernest Rutherford got his students to have another look at an experiment. They took, because it wasn't him, they took a very thin sheet of gold foil. They used gold because as a metal, it's easy to extrude into a thin sheet without it breaking. And he thought, right, well, I'll get them to just fire some alpha particles at it. And we're going to talk about alpha particles a lot later in this course. But alpha particles are positively charged particles. They're in fact the nucleus of a helium atom. So he thought, let's just fire these at some gold foil. What should happen is the foil is nice and thin. They should get straight through. They will punch through this gold foil. Hey, I wonder if we'll get some teeny tiny holes in the foil. Let's have a look at this. So he did this experiment. Then unfortunately, that didn't happen. He actually found that the alpha particles went through as expected, but some of them bounced back and some of them deflected. And eventually he realized that the majority of an atom is simply empty space. There's like nothing there. And we'll talk about that more in a moment. After Ernst Rutherford, along came Niels Bohr, again a very short time afterwards, a couple of years afterwards, and he looked at the electrons and he decided that, well, hang on a minute, Rutherford said that these electrons just orbit around the outside of this tiny, tiny, tiny positive nucleus, just randomly. But Niels Bohr decided that no, he was going to have a look at the electrons, and they actually follow specific rigid rules, and they follow proper orbital paths, a bit like a solar system. And this, again, will become important in lesson 3. After that, Erwin Schrödinger and Heisenberg came along and developed the quantum mechanics model of the atom, which isn't covered in this course. You'll probably be glad to know if you finally ever do look into quantum mechanics. Essentially, it says that, yes, Niels Bohr, they do follow these rigid rules, but not as rigid as you believe. Now, it does mean that an electron can only be here or here or here, but actually it's in all those places at the same time until you actually find it. And if you do find it and find out where it is, you don't actually know how fast it's going. And if you do know how fast it's going, you don't know where it is. Quantum mechanics is weird, but fascinating. And that's one of the beautiful things about physics. These models build upon each other and they get better and better and better, more and more refined. And if you want to look up Schrödinger, please do. You've probably heard his name about his torturous cat experiment where he shoves a cat in a box with a radioactive source and he can't decide if it's alive or dead. So he decides that actually it's both alive and dead until I look in a box. Ha! Oh, kitty cat is dead. But don't worry, he didn't really do that. It's a thought experiment. Or so he said. So here we go. Here is our atomic theory through the ages. We started out with hard spherical balls as our atomic model. These spheres would just sit next to each other and interact, but nothing could change them really. They just were what they were. And then J.J. Thomson came along and went, aha, nope. No. There's little tiny things inside it called electrons. So therefore they must be dotted around this hard sphere. And then Rutherford went, don't be silly. If I fired alpha particle at these, something else would happen. But this weird thing just happened. So it must all be empty space with a positive nucleus. We'll talk more about that in a moment. And then Niels Bohr came along, developed the atomic theory, and then Erwin Schrödinger came along and messed up everybody's life forever. So let's have a quick look then at the Rutherford experiment. Rutherford fired alpha particles, which are very small charged particles, but in the atomic world actually they're quite big. They consist of 2 protons and 2 neutrons, words that hopefully mean something to you, but they will do by the end of this lesson. So these alpha particles get fired off at this sheet of gold. Phew! And what should happen is it should have gone straight through and possibly punched a hole through the gold foil. But it didn't. At least a lot of it did. It just went straight through with no effect. Now gold particles are massive compared to the alpha particles, which are tiny. The gold particles are huge. And so you should either have had all of the alpha particles being blocked and bouncing back again, or they should have all just gone through because the gold foil was really thin. But what actually happened was some bounced back completely. And most of them passed through. This wasn't okay. They should have done either one or the other, not both. And so few of them bounced completely back that it almost seemed like a very low chance of it doing so. But then the kicker was some of the particles didn't go straight through. They went straight, got to the gold foil, and then bent down or upwards. They were deflected. These were positive particles. And so all of a sudden, we realized that these positive particles were coming up against bigger positive particles, but not that big. The gold nuclei are really big for a nucleus, but actually, in terms of the actual atom itself, still incredibly tiny. So these alpha particles were coming along. Some of them, a very low chance, a very low number, were hitting the center of the atom, the nucleus, and bouncing completely back. Some of them were getting close to the nucleus. Positive things don't like to be next to positive things, so they were being pushed away. But a lot of them did pass through, which meant that actually it was all empty space. You had the electrons floating around on the outside, but most of the mass, the main part of the atom, was mostly in the center, a very, very small part. And we'll look at how small in a moment. So they decided most of the atom is empty, but the center is a tiny positive core. And let's see how tiny. So here this is in a bit more graphical detail. If you've already done this at school, you would have probably drawn this diagram in your book or stuck it in your book, but we can't do that. If you want to draw it, please do. It's exciting. So these atoms in the middle represent the gold atoms. Those dotted lines are the helium nuclei, the alpha particles. They are being blasted through the gold. Most of them, as you can see, are passing straight through, but very, very few of them are bouncing back again. And a number of them are being deflected, both up or down. And so this leads us to believe that actually the tiny, tiny cores are positively charged. So Rutherford said, aha, I know, there's these very, very tiny positive balls in the middle of the atom, and then outside there's the electrons, but the most of it in the middle is empty space. This is a picture of the O2 Arena in London. Hopefully you've been there, or you'll have a chance to go there or somewhere like there in the future. It's a fantastic place. I have seen the Legends Iron Maiden at the O2 Arena. So the nucleus, which is where actually, we'll look at this in a minute, where all of the mass of the atom is, sat in the centre of this vast empty array of nothingness. And we come back to our analogy of the universe. It's crazy to think of all of the empty space around us and all of the empty space that makes us up. So the nucleus is 100,000 times smaller than the atom itself. Now, why am I showing you a picture of the O2 Arena? Well, just to put it in context, just to scale, if I took a dot this size, that dot there, and I took that to the O2 Arena and placed it right in the center, and then went back outside again, that dot would represent the nucleus of the atom. The outside of the gargantuan O2 Arena would represent the atom, the outer limit of the electron. You can do this as well with a football stadium or a cricket pitch. If you think about a football stadium like Old Trafford, if you put a tiny dot into the middle of the centre circle, and then you look up at the stands, where the edges of the stands are, the far reaches of the goal end stands, that would be where you would find the electrons. That's the scale of these atoms. There's absolute nothingness, but this tiny, tiny, massively dense point of matter, all of the mass in this tiny point, surrounded by these negatively charged electrons, very, very far away. So here we go. This is our modern understanding of the atom. And I say the current structure and the modern idea of an atom, because as we've seen, these things change. New ideas are developed and we come up and see different realities. And so we find the nucleus sat in the middle. Now, we didn't talk about James Chadwick. Chadwick said, hang on a minute, if I've got these positively charged particles sat next to each other, I know that positives and positives don't like to be next to each other. They're just going to push apart constantly and explode. So atoms wouldn't be stable. There must be something holding them together. And so they came up with the idea of the neutron. The neutron is neutrally charged. It has no charge whatsoever, and it just sits there like glue, holding these protons together, because the force holding these particles together is much more than the force pushing them apart, and the neutrons help that. So we have these protons and neutrons sat together in that very, very tiny space, and the electrons buzzing around outside them. It's very important at the moment to notice that we can't draw scale atoms. We cannot have bits of paper the size of the O2 Arena to draw our electrons and then have a small bit in the middle to draw our nucleus. No. So we have to be able to scale down and draw this, which is a representation of the atom. Try to remember that when you're doing your exams. So we've got the positively charged protons. They sit with the neutrons in the nucleus. These are called nucleons. But let's have a quick look. How small are these subatomic particles? Well, look at these numbers. They're tiny. A proton weighs 1.67 times 10 to the minus 27 kilograms. That's a ridiculously small number. It's also a ridiculously hard number to remember. And the charge on a proton is 1.602 times 10 to the minus 19 coulombs. That's again a ridiculously small number and a hard number to remember. Now, when you do A-level physics, you will need to remember some of these. Well, actually, even then, they give it to you on a data sheet. But why would we have to remember all these numbers? Look, they're the same. The mass of the proton and the neutron are the same. The charge of the electron and the proton are the same. Just one's positive and one's negative. Why am I bothering all these numbers? In fact, we don't. We simplify things like this. We basically say the mass of an electron is teeny tiny. It's about 1 over 1,800 or something. Almost 2,000th the size of a proton. Very, very tiny. Negligible. No one even cares about the mass of an electron. Its charge, we say, is -1 because we take charge to one charge to be 1.6 times 10 to the minus 19. So a charge of -1 is the charge of an electron. Protons and neutrons weigh the same. They have a relative mass of 1. We ignore the ridiculously silly number, 10 to the minus 27, blah, 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 blah. So we just say it's 1. But notice that the proton and neutron have a mass of 1, and the electron is about 2,000 times smaller. When we think about the mass of an atom, we completely ignore the mass of the electrons because you need 1,840 of them before they even add up to 1 mass of a proton or a neutron. So we just ignore them, really. And so the other thing you need to know is that the proton and the neutron exist in the nucleus of the atom, and the electron floats around outside it. So let's have another quick look at the lesson that we have covered. We have been able to describe the structure of an atom. We know now that you have a nucleus surrounded by electrons, and that the nucleus is tiny and the electrons are teeny tiny particles that flit around miles away. I've told you that the mass of an atom is at the center. It's all in the nucleus. The electrons are irrelevant when it comes to the mass of the atom. Atoms and small molecules are tiny. We have looked at the early models of the atoms, right the way from Democritus's thought experiment, I can't chop this thing any smaller, all the way up to John Dalton 2,200 years later talking about his balls. And then you've got Thomson coming up after that saying, nope, these balls have electric bits in them. I have electric balls. Hurrah! And then Rutherford going, well, actually, no, your balls are empty and it's teeny tiny. You have teeny tiny balls, mostly empty space. And then you have Niels Bohr coming along going, yes, tiny balls, empty space, and then shells and orbitals. And then Schrödinger coming along and just going, well, actually, they're just all real weird maths. It's real weird maths. So that's the early model of the atom. And we've looked at why our model of the atom changes. At each step, we've gone from thought experiment, where you can't prove anything, to Dalton 2,000 years later doing rudimentary science, breaking things down in bubbly tubes, probably like a weird mad chemist. And then later on, you get fantastical leaps in technology, and then physicists coming along with a magical electrical contraption, doing all kinds of wonderful things and proving new science. So our model of the atom changes as we change our technology, and so our understanding of the world changes as our technology changes, and that is why science is important. So join me for the next video where we're going to be looking inside the atom itself, and I'm going to talk to you about isotopes, the magical, wonderful thing that helps us understand how old things are. And I'm going to talk to you a little bit about that. So have a look at the next video. I do recommend watching this as a playlist. And also, if you get a little bit bored of the science, feel free to click on this button and watch me open some Pokemon cards instead. All right, stay safe, and I'll see you soon.